Hello. Yeah, welcome to the remote sensing and smart tech session for marine litter for the Ocean Decade Laboratory satellite activity. I think we're all here. Good morning, good evening, wherever you are in the world. And today we have already had the first session. It was a really interesting session. We have a very high standard of presentation and presentations and sharing. We're hoping to match that in terms of fluidity of the session and interest of the talks and the questions. I have a couple of small announcements to do about this session. The event will be recorded and is now live in YouTube. For those who want, the attendees' mic and camera will be off at all the time. And if you have any questions to the speakers and comments for the end of this session, please do so in the link below on a Padlet. This will be repeated. All the links to the YouTube channel and to the Padlet will be repeated in the chat. So just to go back into what are the objectives of this satellite activity, well, we wanted to, we have a very dynamic group of people who are in the International Ocean Color Coordinating Group, who are, and there is a task force there, and we are putting together this satellite activity to collect the users and stakeholders' expectations to see what users require, and that was discussed in the first session, but also to give an update on the technologies and techniques and the results and the state of the art of the current science on marine litter detection from remote sensing methods. And this is this session and tomorrow morning session. So please stay tuned if you want to learn more what you can do with satellites. There was a lot of people asking these questions this morning. I hope they're here today as well. And finally, we want also to collect or to create a collective vision towards the future on what is the way forward. What are the activities that we have been looking at so far? What is the results that we have at the moment? What are the things that need to be done to fulfill the users' interest and expectations, and to match the expectations with what really can be done at the moment. So I hope it will be an informative and really exciting session this afternoon. The speakers indeed I'm sure they're going to give a very good overview, each one of them. Manuel, Arias from ICM CSIC, and Shungu, Garaba from the Institute of Chemistry and Biology in Germany, in Oldenburg. They will speak of the high level and policy things that we'll be trying to articulate in the community. And Professor Chuanmin Hu has a long career in remote sensing of floating materials from macroalgae into marine litter, and he will also give us an excellent review. And then Els, also from VITO in Belgium, who has really exciting results from laboratory and possibly in situ sampling from different platforms. And so we have 15 minutes per speaker. We have also a special invited person in the middle to break away from all this very serious science. I hope you will enjoy also that. And please conserve your questions for the end of the session, and please have a look at the Padlet between sessions or between speakers if you can, and try to fill in with your thoughts and comments on the sections provided there. And without further ado, Please, Manuel.
Yes, can you hear me and see me properly?
I can definitely hear you. Your presentation.
Yes. Okay. So if it's still visible, right?
Sorry?
Yeah, it's still visible in full mode.
We cannot see your presentation at the moment.
Okay, that's what I was asking. Okay, 1 second. Okay, and now?
Now, yes, just need to.
Yes. Okay. Great.
Thank
Okay,
you.
sorry for the glitch. Okay, so first of all, thank you very much to all of you for attending today and having some minutes to listen to our people and all the presentations that we're going to have today. I'm going to start the technical presentations for today with an introductory set of slides related to detecting of marine plastic debris with satellites. And the first thing I wanted to mention today is well, probably something that everybody already knows, is what is the marine litter. And the reason why I bring this information is because of marine litter is not particularly a simple element to track with any remote sensing techniques, whereas drones, airplanes, or satellites, because of the large variety of compounds and elements that it has and the different spatial scales that it takes. So we have litter from pieces of litter from millimeters to even centimeters or even meters. And we can find it in the surface of the ocean, on the beaches, and even in the bottom of the seas. In terms of volumes, what we can do currently with remote sensing is just monitoring a part of the total pollution. So it is estimated that around 8 million metric tons per year enter in our oceans. And of those, only just a small fraction really remains in the surface. This is what we are calling right now the detectable compound of the marine litter, which is just the floating elements, and it is around 6,000 to 245,000 metric tons per year, which, as you can see, is just a part. The rest of it, it disappears once it enters in the ocean, in the sense that it goes to the water column or sinks directly to the seafloor, and is not observable by aerial remote sensing. There are other techniques for remote sensing that can be called the submarine remote sensing techniques that could have possibilities to monitor these elements. But our focus in this presentation is just going to be based in platforms that are aerial platforms or spatial platforms. Said all of this, one of the main questions that we face is why we need remote sensing to monitor marine litter. And this morning, we have seen interesting talks about existing services and stakeholders providing the needs from the community. And one of the key elements that has been seen is that the current in situ observations of marine litter are quite scarce and sparse on time and space. So quite often, it is not easy to gather systematic information from plastic marine litter that can be then used by models or tools or services to provide the level of information that decision-making organisms need, or that entities, industry, companies, or name it, organizations could really require. In the slide, in the left image, this is just a well-established publication from Eric Van Seville in 2015, in which he ran a comparison of the results between different numerical models that they were trying to simulate the densities and concentrations of different marine litter compounds throughout the oceans by using a stable Lagrangian transport. The main issue, as you can see in this plot, is that the results between the models can differ between them in a factor of 10 or even 100 times in terms of concentrations, some models are not very similar each other. And large part of the differences between these models happen because of the small quantity of data that they have to ingest into the models and do a proper simulation. In this sense, what remote sensing can provide to scientists is the concentrations and help to determine the transport dynamics of ocean plastics on the larger scale. And many of the questions actually related to the spatial distribution and in what domains the marine plastic litter is sending are still open. And remote sensing can inform about data gaps that are existing in respect to the in-situ observations that the community is collecting around the world. This is very relevant for modelers because of modelers, as I said before, they need much more data in order to constrain the results of their models. And at the same time, they also need data to validate and properly determine the accuracy and errors of the models. This is one of the areas where remote sensing can help by providing more systematic routing and global coverage of data of marine litter, and in particular marine plastic litter. This is also of use for policymakers because of when we introduce regulations or policies to control or mitigate the problem of plastic pollution at the oceans, there is need to check whether these actions are actually having impact in terms of the plastic pollution at the ocean. And to do that, you need routine and again systematic indicators or parameters that you can observe and you can study to make sure that these measurements are being effective. And finally, what we are calling ocean cleaners, or these sets of well-known organizations that are working in trying to clean the oceans out of this plastic pollution, they need this type of data to localize or locate the accumulation zones so they can focus or make better use of their resources for a more effective cleaning, as well as to assess the effectiveness of such cleaning strategies in order to evaluate whether they need to readapt what they are doing for an optimal output. And the challenge for remote sensing of marine litter, part of it I already mentioned it, is related to the large and wide variety of composition as well as sizes that the litter it has, which make it quite complex to detect from many different types of remote sensing technologies. And the reason being is because of most of the remote sensing technologies look to a specific particular physical properties of the items or substances under observation. And when you have a diversity of them, both in spatial scales and both in composition, it becomes more complex to find a single solution able to provide all the information that is needed. In this area, we are contemplating that according to the fraction of the marine plastic litter that we are considering, we can go from optical spectral techniques like visible infrared, laser-based techniques like LiDAR, it could be an option, to high spatial resolution imagery. Whenever you need to do identifications of single items, is almost the only way to do it, and to microwave-based techniques like radar and passive radiometers, which might have some potential to inform about densities or concentrations of microplastics or smaller fractions around the ocean. In terms of the ongoing research and development activities, the community of remote sensing is making use of a lot of tools to improve and develop the current techniques. One is to get support from transport models. So even if we feed data to the models, we also use those models to better understand the dynamics of the marine plastic contamination in a way that can help us to understand what are the best targets of opportunity or strategic targets for detection with remote sensing techniques. On the other hand, we have also to develop substantial laboratory measurements for different physical properties of this marine litter in order to understand what are the physical properties that offer the best opportunity to be detected using the current technologies that we have. Other aspects that are very important is to better understand how these properties, this signal from the different compounds of the marine can be seen throughout the different types of platforms. So we have sensors and platforms. Sensors are related to technologies for detection, optical, radar, etc., whereas platforms are related to the devices that are carrying these sensors, which namely can be drones, airplanes, or satellites in the case of aerial remote sensing. And these platforms, depending on their altitude, they might need support from physical modeling to better understand the signal that they are observing at the altitudes that they are operating. This is an important aspect to be taken into account in remote sensing. The other important aspect is the deployment of targets and for validation and training of retrieval models, as seen also in these photographies, where we, the scientists and the community working in remote sensing, we try to understand how this signal operates and also how we can improve our retrieval algorithms to achieve affordable detection of the marine plastic litter in our oceans. In terms of capabilities and efforts, I'm putting now a number of examples of what we are doing currently with remote sensing. In this case, we are talking about imagery from satellites. This is spectral data from Sentinel-2, and this is a good example of reported in the literature technique to detect accumulations of floating plastic in the bay and region of Honduras. So in the Caribbean Sea, there are a lot of inputs of plastics coming from rivers, and this group from Kikaki in Greece, they have developed a technique that is able to identify these filaments of floating plastic material, and that allows for mapping, geographical mapping of the presence of this litter, and to report of hotspots and events that are producing them. The advantage of Sentinel-2 or Landsat 8 techniques is that the spatial resolution is quite high, between 20 and 10 meters. And this is a very affordable spatial scale for many services and needs from end users. More on this, we can also explore the use of remote sensing to detect proxies of presence of plastic pollution. So in this case, this is a study from Arias, from myself, and the team that we were working together in Arias, in which what we tried to aim here was not to detect directly plastic pollution, rather than identify filaments of floating marine debris with high probability of containing also plastics on it. This technique was developed using spectral indexes, so using the information provided by Sentinel-2, in this case, to devise or to identify pixels in the image with possibility of having floating marine debris, supported with an algorithm of artificial intelligence to produce the classifications of those pixels and enable contextual identifications of those filaments. And with all of this, we are generating a set of a data set of filaments collections. All of these images are in the Mediterranean Sea. That will be soon available to the community for further studies and analysis. And more on this, and this is coming practically hot from the oven. This is a very interesting work from the team of Gudge and Murphy, in which they have used thermal infrared to identify floating plastic in the surface of the seawater. To do this, what they have done is to deploy initially some set of artificial targets, and then produce measurements both in day and night to better understand what is the impact in terms of the heat transfer between atmosphere and the ocean associated to the presence of plastics. And what they have reported is that these transitions of heat between the ocean and the atmosphere are not behaving the same way when you have just the ocean water and when you have a layer of plastic on top of it. So this differential in the thermal infrared information can be used effectively to detect floating plastic litter. And this is perhaps more known. There is also the opportunity to use very high resolution satellites. And this type of platforms have a very high spatial resolution. We are talking of the scales between 15 or even 30 centimeters, which can be used for actual recognition of floating plastic debris over the ocean, but also in coastal areas or directly in beaches. In this case, in this study, which was presented by Acuña Ruz et al. In 2018, what they did, it was use a constellation of Worldview 3 in order to study the accumulations of big chunks of plastics present in the beaches of Chile. And similar techniques has been already developed with drones, which are very promising for cataloging and identifying and quantifying presence of floating plastic debris that ends up into the beaches of the world. And another recent study, which is preliminary in many ways, is that there is the possibility, even if this is still under significant efforts of studying and development of candidate techniques, to use the signal reflected from the GPS constellation to identify potential accumulations of floating materials in the sea surface. There is still work to do in terms of identifying or trying to separate the signal from the different potential components. But this is also a promising technique that will have many advantages if successful in terms of providing daily and global coverage for low resolution accumulations of floating plastic debris. But as I said, this is still an ongoing work, so please don't take this yet as a consolidated tool, because of it is not. In similar way, we can also use synthetic aperture radar, another active technique on board of satellites or airplanes, in which we use the reflected signal of radars over the sea surface to try to find the patterns in the roughness of that surface that can be linked to the presence of floating materials. In this case, it is a very interesting combination of synthetic aperture radar and artificial intelligence, where combining information from the SAR and also from training data set generated from optical data sets, one can generate a machine learning tool that is able to classify within the SAR with high spatial resolution potential accumulations of floating plastic debris. So going in summary in my presentation, in terms of needs, remote sensing technologies are the solely affordable tools able to provide systematic observations of marine litter, plastic litter at global scale in variable time scales. It complements quite well in situ observations, which are always necessary, both for the development and validation, and bridges the gaps in data supporting the modeling effort. In terms of capability, remote sensing can inform of plastic litter using sensors from kilometric spatial resolutions to centimetric spatial resolutions, for example, satellite to drones. And similarly, remote sensing is proving able to inform in multiple plastic fractions and accumulations, but having in mind that satellite-based solutions are unlikely to report on individual items rather than densities or concentrations. For individual item recognitions, other techniques like airplanes or drones are much better suited for this. The limitations is that no sensor or technology is perfect for the purposes of marine plastic litter, with some being particularly challenging or having specific limitations. For instance, optical remote sensing can only operate during the day and when the clouds are not present, which is, for example, a very good delimitation of this type of data sets. And current results for satellites are still not mature for operational purposes. There is need of significant research and development effort. To conclude, the way forward from our side, from our group, in terms of the remote sensing development, is that the use of remote sensing for marine plastic litter is an emerging technology and not only requires still significant support from organizations, governments, and institutions to continue developing and reach an operational level. This is more true for the satellite side of the things. For drones, the situation is much more mature, but still drones will continue to be limited in terms of the size of the areas and times that they can operate. So satellites are still on need. The complementarity of the availability of remote sensing technologies calls for encouraging the merging of various of them as optimal solutions for a global monitoring of the marine plastic litter in all its complex nature and behavior. It is not possible to just use one single technique to get an optimal mapping. Eventually, we'll have to merge different technologies, potentially from different platforms, in order to improve the coverage both in space and time and the accuracy of the measurements. Moreover, artificial intelligence and machine learning are also areas that we need to continue to introduce in this context, because they are very well suited to extract useful information from complex data and for fast processing of large volumes of measurements. Future floating plastic detection, classification, and identification will be substantially linked to these other technologies. And as I have been saying today in this presentation, there are already many initiatives that they are introducing elements of this artificial intelligence in order to afford detection. Continuous exchanges with the stakeholders and societal users of this data and the right services is essential to arrange needs with capabilities and to help shaping the technological roadmap leading to the optimal solution. And who knows, maybe having dedicated satellites in the future for this purpose. And with all this, I think I'm finishing my presentation, and I want to thank you all for your time.
Thank you very much, Manuel. You're in relatively good timing. The questions, please put the questions in the Padlet as well as your comments there. So let's hope that is all okay for you. Then I'd like to call Shungu to take the screen. Okay, are you there ready?
Yes. Can you see my screen?
Yes, we can see and we can hear. Go for it.
Okay, so thank you, Victor, for the nice introduction. And well, thank you everyone for tuning in. And yeah, so my presentation is more of an overview of what we have been doing over the last maybe 1 or 2 years, in the sense of trying to form a coordinated, or like to have a group of experts coming together and having one voice in terms of what we are doing towards remote sensing of marine litter and debris. And yeah, so what is the problem? Everyone knows the problem, and it is, yeah, omnipresent in the worst places, the good places, even in Hawaii, the nice holiday place. So this was a beaching event in Kailua in Hawaii recently, like I think this was last year. And in another example here, this is Cambodia. You see packaging plastics, and just behind here, let's see if I can also put my pointer. So just behind here, there's a restaurant. So you can imagine all their packaging material is just being thrown here. And then here you have like residential accommodation, whether, and in most cases, this is mismanaged plastic. So the motivation, like for us to be using remote sensing, I think this table nicely summarizes it. And this is like from the IOCCG report 17, or the 2018 report. So if you really do the math or like the finances, when you're using remote sensing, you have the advantage of spatial coverage. So you have spatial coverage, you have low cost per end user, you know, like relative cost per unit area or per end user would be very low. So that's one of the motivation that has brought us, you know, like to come up with or to start working on the topic of remote sensing of marine litter. So of course, here I try to give the same impression we have here. So with the point measurements using net rows over the years, like since the 1970s, when they're like some of the first reports or that are in open access, they have been collecting data in more or less the same approach where, you know, you have a net row, you collect data, but these are limited to, in most cases, 30 minutes. You have a net throw survey of 30 minutes covering, with a net which is opening with 50 centimeters and 1 meter wide, or in some cases wider. But generally, these are considered more or less like in situ observations. Of course, the value or the amount of information you can gather based on observations, like from net throw or like point measurements, it is very high. You can do lab analysis, weather analysis, but then when you go to remote sensing, like when you start using drones and satellites, then of course you have limited information, but you get to understand the spatial distribution of plastics. And in some cases, depending on sensor capability, you can also get some information about patches. So in the next slide, this also summarizes the point I was trying to explain here. So here, I think everyone in the audience has an idea of what we talk about when we say microplastics and macroplastics. So here is like an example from the GESAM report, where it tries to just, this is from Ryan et al., but this is also available in the GESAM report. So the megaplastics, anything higher than 1 meter, but in most cases, the discussion is always about microplastics and macroplastics, with the limitation of 5 millimeter being the diameter grade. So the abundance, of course, when you go to the smaller sizes, the abundance is growing. And the mass, of course, if you have the bigger plastics, they have more mass compared to the smaller plastics. And the environmental risk, of course, ingestion, when you have the smaller size plastics, marine life, fish, or like other microorganisms in the ocean, they might confuse the smaller plastics for food. And then with the bigger plastics, you have challenges of entanglement. Same story that is happening with sampling. When you're sampling, of course, sampling right now, due to technical limitations, we are up to maybe like the mesh size of net throws. But then, of course, the limit is going up towards, like the bigger pieces you can pick by hand or other devices. Same as information of origin, you can still get more information related to origin of plastic or litter when you have bigger pieces. Then of course, it's easier to also mitigate the bigger pieces. So now, like to the point of remote sensing, we are still trying to understand, so this is ongoing research, and this is why we want to coordinate things so that if we are talking about an approach or method, it is validated, and the community, from experts to the scientists to citizens, they have an understanding of what is going on, and we are using the same terminology, the same approaches, and we have a universal understanding, or close to a universal understanding. And so when at the moment, what some of the studies have been showing, like the ease of remote sensing is relatively, it's simpler, or like, we have managed to do proof of concept, and we have also come up with different methodologies that have been tested, and they continue being tested and validated. So at the moment, we are still in the field or in the open ocean. We can safely say we can observe aggregated patches, windrows, and artificial targets. Then of course the question, how big are the patches? That's still like an ongoing research question. So like, as I was saying, we need a coordinated voice. And just to give you like an overview or history of where things started, as far as I know, of course, I apologize if someone is in the crowd who knows anything beyond 2016, but I should research more on that. But so since 2016, there has been some work that, which has brought so many experts together. So this started with a workshop in Hawaii, which was hosted by Nikolai Maximenko. And then from then on, there was like another group of scientists in Europe that was hosted by European Space Agency, thanks to Paolo Corradi, who was behind some of the organizing and motivating the activities. And then in 2018, there was a meeting with the SCORE and Flotsam group, which also brought forward, like new ideas and activities. And from all these activities in 2019, that's when, like the community came together to come to start writing white papers on how best to proceed and where are the scientific gaps, where are the, like the low-hanging fruits, and what else should we go beyond the low-hanging fruits. So there was a paper which was led by Victor, and this is also in open access. So I have to mention this is on open access, and as well, this paper was led by Nikolai Maximenko. It's also in open access. And in 2020, that's when we saw, like, I would say, large amounts of like funding or resources being mobilized by different agencies. So just to mention a few, the Portuguese space agency, they put forward €500,000 towards a study of using artificial intelligence and combining artificial intelligence to understand how best we can also try to reduce marine litter, well, not reduce, but detect and or study marine litter using space or remote sensing technologies. Similar in the United States, the NASA also, through the ROSES project, they have funded 3 projects which are already started this year. And ESA has also been putting so much effort towards different studies that are related to marine litter, using resources from space and using technologies like artificial intelligence. And also in 2020, there was a community white paper, or like community paper, a review, which is also in open access, which was led by Eric Bansebil. So this figure, I like this figure. Well, yeah, I'm also responsible for the figure, but I like the figure because it gives a nice overview of the different technologies, platforms, and tools that we are using to really try to push the science ahead by understanding how remote sensing can support and maybe also like, well, provide information to the community, be it any, well, let's just say stakeholders. So we have scientists or like citizens who can also like put cameras on ships, or this could be ships of opportunity or dedicated research vessels. We have people, and we have had presentations of people talking about the use of drones. And we have some studies where there's use of aircrafts or aircrafts of opportunity, and also like the new technology which is coming up, high altitude pseudo satellites. And then of course, the final like platform that is we can launch from Earth using satellites or CubeSats. And then of course, there's also fixed observatories that like could be cameras on beaches, and all these platforms. And in this picture, it also gives you an idea like what the height at which we are observing things, and also like this aerial coverage that you observe. And here we also have to validate what we are observing. So that's where you see the impression of like net trolls behind the ship. So far we have, we have conducted different discussions or networking events where we have more or less summarized. So this is a summary, but it's not exhaustive. But the main goals, or what we think the community is asking for. But of course, you're welcome to help us revise this and make this a comprehensive understanding of what the stakeholders are requiring or expecting from remote sensing. But the main thing is, at the moment, what we have, what we can say from based on scientific studies and proof of concept. So there is detection. So the detection component involves like people might be interested in only the shape, color, or size of the object, so as descriptors. And this can be obtained from any form of RGB camera, so be it from a phone, be it from a GoPro. So this is easily done using drones or smartphones or other like platforms with RGB information. But then if you want to identify, of course, for some stakeholders, it is very critical to know the type of polymers. Of course, this could be also influential for policy making and coming up with action plans, or rather changing the policies or regulations in different states, member states. So the question is identification of the polymers. And then for this identification or distinguishing of polymers, you would require FTIR, which is Fourier transform infrared, Raman spectroscopy, and shortwave infrared. And in some cases, you saw the previous example of thermo-infrared technology being used. And then when it comes to the quantification, one thing I have to point out with remote sensing, if you're going to look at the ocean surface from above, of course, you would have the limitation of seeing what is at the surface. So the limitation of seeing what is at the surface, you don't know what's below the surface. If you have floating material, you might have some material. So in this picture, if you look closely in this picture, you will likely, well, in this case, I know, I am 100% sure, like there were other plastics below. So with remote sensing, you only see what is on the surface, but you don't know what is below. And the one way you can quantify would be actually, well, you could do actual counts, but from remote sensing, you might be interested in pixel coverage, knowing your pixel is 20 meter by 20 meter, or your pixel is 100 meter by 100 meter. So you either put a percentage to that, or you put a number in terms of like aerial coverage you can calculate from the pixel. And then when you want to study where things are coming from, where they are going, where they are, and like for dedicated cleanup activities, you need to track things. And that's where also, like if you have geostationary satellites that are looking at one location over a time, you can track things. Or if you have like regular drone surveys or fixed platforms, that's where they come into play. So this will be tracking where things are going, where they are coming from, and also support like dedicated cleanup activities where you'd easily identify location of litter or big patches, and then you can send volunteers or dedicated cleanup teams to clean up like litter. Going on, so we have come up with a task force, and like as I was speaking about earlier on, in terms of having a unified or standardized way of doing things and coordinated by one body of a group of experts. And within the IOCCG, we managed to come up with a team of experts from space agencies, companies like industry, foundations, research institutes, and universities. So I think here the main message here is we have tried to come up with a diverse group of experts who are working towards the topic of remote sensing of marine litter. And just to give you, to put names to faces. Here, the team is led by, like coordinate, or like the team at front. We have agency representatives, starting with Paolo Corradi from European Space Agency, and we have Laura Lorenzani from NASA, Debashish Mitra from ISRO, and then we have Hiroshi Murakami from JAXA, and then myself as one of the scientific coordinators, so one of the co-chairs. And again, to repeat, the task force, the primary goal is to coordinate the advancements of like what is currently available, like what is available at the moment in terms of remote sensing technology, be it from drones, be it from space tools. And then we come up with more or less like a roadmap or like ideas or recommendations of what possible like dedicated or rather interdisciplinary tools that might be launched in future, what they might require or what they should have to support, like remote sensing of marine litter. And of course, like the other point is in all aquatic, like our dedication is on all aquatic environments, but this can also be extended to land, or in most cases like beach or like coastal areas where you tend to have beaching of washed or maybe washed ashore plastic litter. And also, like we have split the team, so like to coordinate different activities. I'll explain this later. Just to put names again to faces to names. We have Manuel Arias, Lauren Bierman, Francois Regis Martin Luzier is one of the founding members, and Victor Martinez-Vicente. And just also, well, I'll just give you maybe a second to also write down the link. It would be nice if you can have a look if you're interested. So we have created a one-stop, like I would like to call, I think the right way we called it is a one-stop shop of, like if anyone is for stakeholders in remote sensing of marine litter and debris. So this is where we hope and believe that like any information related to remote sensing of marine litter should be found in this on this website. So just a brief history of the task force. So this kicked off, like the kickoff meeting was in January, and we launched the website, and like we introduced the different members. And then in April, things started to move, and we had a bi-monthly meeting of the coordinators and the co-chairs. And we had and I'm very proud to say, like, we managed to have our first workshop, and we should be having our second workshop very soon, and announcements will be coming soon if it's open to everyone. One other thing, like, well, not one other thing, but like the one-stop shop title I've been giving, and one thing also to note is the living library bibliography. Why do we call it the living bibliography? We are trying to create a source of information for anyone, like be it citizens, be it scientists, be it stakeholders, where they can find in one place information related to remote sensing of marine litter. So how have we done that? So since November 2021, we have about 60 papers, like just references. So here you'll find references related to the topic. Of course, there are other papers out there. We are still looking, and we encourage everyone to submit. Like if you go on our website, on the task force website, we have a simple like set of rules on how to submit. It's just like the referencing style so that everything is consistent. And also like data sets. If you have data sets you want to share with others, kindly just send us the reference so that anyone who might be interested in your data set that is related to remote sensing of marine litter or debris can always find it here. So again, please kindly share your data and information so that we know you have published something, and then others might be interested in that study. So thank you again if you submit something. Again, so the point, again, what I just explained, like our main theme or goal is to promote open access science, and we are also promoting the FAIR policy. And on our website as well, we do not say like you have to submit your data to this particular open online repository, but rather we provide you a list of repositories where other scientists have submitted their data. And I think one of the presentation will go into more detail, like Ocean Scan will talk about like a dedicated database where people can submit data related to remote sensing of marine litter. Yeah, so one other thing is I was showing you the timeline. I'm also happy to announce that, like the agencies and different stakeholders have been investing so much money into trying to understand, like trying to explore and try to advance the science in remote sensing of marine litter. And so the different agencies so far, they have funded around over 30 research projects. So in the coming year and coming years, we should be getting results. And like I would say, watch this space. You should be having wonderful news or updates related to the topic. The previous slide, I was talking about the different coordinators, different groups. So within the task force, we have not split, but we work in conjunction with, in parallel. I would say, yeah, okay, we are pillars. The pillars of the task force are, we have called them core topics. So these core topics work independently, but then we have one way to bring everything together, which is the international experts. But we have Victor, he's leading the technologies. So trying to understand what technologies are available, how can we utilize these technologies, what information they can provide, and then maybe also try to find the gap. Where is the gap in the technologies that are already available? How can we like recommend the agencies or stakeholders who design instrumentation to provide the tools that we require for our science in terms of like remote sensing of marine litter? So once we get the technologies, of course, then we go to data sets. So once you have the data sets, we then go to algorithms and applications. So how do we convert the data we're getting into information that is useful to policymakers, to citizens, to different, like one example is how can it be useful to port authorities? There was a presentation on port from a port authority. And then also like for fisheries, aquatic, for fisheries, how can that information be useful? How can we present or provide useful information? And how do we connect all this information to interdisciplinary activities? That's where Lauren Bierman is also working on, like how to connect the products we are generating from remote sensing, how they can be disseminated to the community. And of course, one thing I forgot, the teams are either they have regular meetings, and then also they are working towards a draft. Again, the term I have to emphasize here, living reports. So these reports would be like similar to Wikipedia type of documents where we try to update them with changes because technology is evolving and things are moving very fast. So unfortunately, the evolution of technology and the amount of plastic is just not equal. So that's why we decided to do living reports, because all these things, as technology is evolving and the amount of plastic is changing and the diversity in plastic is changing. So all these things have to be updated, and the timeline is always just, it's unpredictable. So just to summarize everything, well, the most point is the most important point is space agencies and funding sources. They should fund more advanced add-on works related to remote sensing of marine litter. So that means, like new research work should actually, well, I don't know if it's the right word, like we should not try to reinvent the wheel, but rather build on what is already out there. So that's why also like we see the task force as one source of such information. So it would be very nice, or like it would be vital, so like for funding agencies and also for scientists outside who are trying to study remote sensing of marine litter, to get an understanding of what the task force or related projects have been working on, and obviously some of the results, so that we try to build off other technology which is already there, and then we advance the field instead of doing the same thing over and over again. And then, of course, use the knowledge base from the task force to identify, of course, the technology and research gaps, be it also algorithms and how other ways we can utilize the information we are collecting. And right now, like one of the things is pushing and exploring new initiatives. So there's also like the use of airborne monitoring as a synergy with other technologies, and promote potential remonitoring applications at regional level. So like different parts of the world conducting regional level observations, or be it local level as well. And then one thing, of course, for remote sensing, at the end of the day, we need validation. Of course, we can do lab observations, we can do field observations, proof of concept, but at higher altitude remote sensing, we still require, well, ground truth or sea truth information. And of course, the operative goal from ongoing research would be like how we can realistically detect X or Y if we had a sensor Z. So in order to achieve W, which is needed to effectively support K. So, like the whole idea of doing the task force is try to coordinate such activities whereby we can identify the gaps and also identify the capabilities of the current tools. And with that, I say thank you for your attention. And well, if there are any questions, I'll be happy to answer them.
Yes, thank you very much, Shungu. Very, very good presentation. I think the questions will be happening at the end of all of the presentations. So we're moving very quickly to the next speaker, and this is kind of a small break in the different in terms of topic, because we're moving away from a little bit of the scientific and scientific policy domain into more of a outreach, just to give you a break of these heavy scientific subjects, but at the same time is moving away from the surface of the ocean into the deep. So I'm very pleased to introduce Ahmed Gabr from ImageIf, who's a world record holder for the deepest scuba dive. I cannot dive that, not even closer to that. So we'll be talking about the activities that he and his team are doing for plastic pollution in the sea. And there you go. Ahmed, When you are ready, the floor is yours.
So I'm sorry. Let me just like cancel the camera because I have a little bit like interruption with the internet here in the country. So I will cancel the camera. Is that possible?
Yeah, cancel
the camera. Yeah. So I mean, like, if you can just like, I have the presentation of ImageIf first. I mean, like, yes. All right. I mean, like, it's a little bit. I mean, like, my story is different. Then I cannot actually compete with the beautiful presentation I just heard right now. But I'm gonna tell you my story about like sustainability. You know, I did my deep dive record in 2014. It was a 6 years project for myself, and then I did my dive. I did my deep scuba dive, which is 332.35 meters, verified and official still to that day, you know, by Guinness Book of Records. And then I started. I mean, like, and during my last part of my deep dive at 27 meters, then I had like a shark. It was with me for 6 hours, you know, and then which is a little bit weird to find a shark in this specific area around. So as well, I mean, like during my diving before and after, I mean, like during my preparation and after my deepest scuba dive record, I realized the coral reef is not as healthy as before. And then so I kind of like realized, and I started to see a problem, you know, like in the ocean in general, you know. So I mean, like, so I teamed up. I mean, like in 2015, just 1 year after, I started, like, I wanted to point this problem out, you know. So I did. I was able to collect 614 divers, and then I did the largest underwater cleanup in a single venue. The most participants in underwater cleanup in a single venue, and that was another Guinness World Record title as well. Like I gained in 2015, like almost 1 year after my deepest scuba dive record. And then the whole idea, it wasn't the record itself. The whole idea was actually like to put the attention into the problem. And then I started, like, I mean, like, I teamed up with my partner right now, Omar Samra. He's also like the first Egyptian like to go to Mount Everest, and he climbed the highest mountain in each continent because he started also to realize the problem like he has around him as well. I mean, like after that, I mean, it's we started like to realize like we have like problem with, especially with the single use plastic. So we're in contact. Me and him were in contact with nature, and we saw like the nature is not the same like before. I mean, like, so our motto. I mean, like we had a motto. I mean, like, so we need to clean up and we need to solve the problem from the deepest, from the bottom of the sea to the mountains. You know, like to the highest mountains. You know, we realize that we have big problem, and the problem is mainly, as mentioned before from the previous speakers, you know, in the nanoplastic. You know, it actually transformed, you know, into more toxic chemicals. Plastic is everywhere on the planet, even in the most remote and protected natural areas, you know, that can be only reached on foot. There is a pieces of plastic as well for every fish in the sea. 700 species are going to extinct. You know, 90% of the seabirds have pieces of plastic in their stomach as well. 48% of the sea creatures have plastic in them. At the depth of 2,000 meters by 2050, there will be like more plastic than fish in the world, the ocean. You know, so we realize the problem is actually with the actual, you know, is with the single-use plastic. The problem is not the plastic. The problem is the single-use plastic is unused, and then we need to change, and we need to sustain it. Like we need to change this single-use plastic to be a sustainable use of plastic. I mean, and there are like a lot of experiences. I mean, like happened around the world. I mean, like it happened as well, like in India and Nigeria, they made like roads, you know, like roads made out of plastic, paving stones as well, like it happens in some African companies, some African countries, rooftops as well. You know, it happens now, especially in Europe. And then we started, like, the name of my company. It's What If, you know, what if if we tackle the plastic crisis in the places in the hardest access our protected nature habitats? What if we could solve the problem of the source from the source? What if we could find a genuine solution for plastic waste? What if we could make fashionable again of the sustainable products? This is our thinking here, you know. So our campaign mainly like based on three phases. The first phase is like to increase the awareness, especially with the younger generation. And this is just by talking, doing workshops in schools, you know, or in the remote areas. The second thing or the second part is actually is to do the solutions by the actual cleanup, which we already did, like especially in places that doesn't have garbage collecting system. The third thing is finding alternatives, you know, like and encourage the local industry, you know, like in Bedouins in remote areas, do workshops with them, you know, like start to give them like workshops, and then start to buy their products and then sell it for them, and then give them profit, and then we make profit as well. This is mainly like our if like, and then as well we made like lately we made the hackathon a competition. We invited artists, you know, from around the country here, and then artists. I mean by artists cinemagraphers, you know, like documentary movie producers, you know, and painters, photographers, you know, from around the country, like, and then to spot the problem, you know, like to spot them, like, and then we give him like prizes, you know, like, and then they started, and then we give him prizes to encourage the other people, I mean, like, and to focus on the problem and increase the awareness by doing all of that. It was kind of successful as well. Like, I'm working on another project right now, you know, which is a coral restoration, you know, like I can see the problem. I mean, like, it's like as well on the coral color as well. I mean, like, it's not the same like before, you know. So corals, and especially in Egypt here, they support human life. Over 500 million people, you know, worldwide rely on reefs for jobs, food, and coral coast defense. They are vital for the development, you know, of new therapeutic approach, like the treatment for cancer and heart disease, which rely on the extract from species living on the reefs. They are vital for supporting the ecosystem. They are also, like, you know, like, to buffer shoreline against 97% of the energy from the waves, storms, and floods, you know, helping to prevent loss of life. So, you know, I mean, like, it's very important. I mean, like, especially here in Egypt, you know, of the coast of Egypt, for example, you know, the water of the Red Sea are home to some of the most productive and diverse coral reefs in the world. Egypt attracts millions of divers, snorkelers, and other coastal visitors from across the globe. This, combined with easy access and travel option, make of the tourism industry one of the biggest contributors to the Egyptian economy, generating around 389 billion Egyptian pounds in 2018, and provide work opportunities for hundreds of thousands of Egyptian people. Since we are blessed, we had to have such an amazing coral reefs providing so much for our economy and people, where exactly there is a problem. So I thought like about having like, you know, like having corals, you know, like around the shoreline of Egypt, you know, like to provide alternative coral reefs, you know, like because we have like very high traffic in that, you know, and we have like too many stressors like also affect these coral reefs. What are these stressors? Like, number one is climate change. Number two is pollution, you know, so I'm doing a lot of cleanups right now. number three as well, you know, like unaware, like people not aware, especially who work in the tourism industry, you know, like they damage coral, they just seek for fast money, you know, by teaching like novice divers, for example. So I imported right now. I mean, like I have like people who does the know-how. I mean, like who did that already, like in other Asian countries. I mean, like, and then right now I'm in contact with the Ministry of Environment, you know, and then we started this project here in Egypt. This is all what I have for now, and wait for me soon. Hopefully, I mean, like I can have more information to give. Thank you very much.
Thank you very much, Ahmed. Very inspirational talk. I think sometimes when we are thinking about our own science and our own satellite algorithms and these problems, we sometimes we lose track of where the real problem are and how far something that begins on the surface can reach to the deeps and to coral reefs and impact on biodiversity and impact then on people's lives and sustains, like they cannot earn the money from the tourists if the tourists are not getting there. So thank you very much for reminding us of all these things with such an insight and beautiful pictures, and looking forward to see more of your prowess and see whether you can do even greater things, like going into greater either depths or with more people to clean up. So thank you very much, Ahmed. And I think we go to the next speaker, who I think it is Professor Chuanmin.
Thank you, Victor. Can you hear me and see me?
Oh, yes. Hello. Good morning to you. Yes, I can see you.
Thank you. Good afternoon. Good evening. Let me try to share my screen.
Yeah. Thank you very much for attending and giving us a presentation today. So we're looking forward.
My pleasure. Thank you. Pointer. Okay, cool. You see my presentation?
Yes, perfect.
Okay, great. First, I want to thank the previous speakers. You guys make my talk much easier for the excellent overview. There are many types of remote sensing techniques, and my talk is focused on the ocean color remote sensing, basically visible near-infrared channels. So I want to convey the message of what is possible, what may be difficult, and what may be even impossible. Okay. So yeah, because of the overview has been covered, so I can go directly to the technical steps. So this is regarding not just marine debris. I use that as the same name for marine litter. It applies to all floating matters on the water surface. So the principle apply to everything. Conceptually, we need 3 steps to detect and quantify the floating matter. One is there something there? Okay, so that is purely based on a spatial anomaly. Once you see, oh, there's something, but the second one would be, what is that? Okay, that will be based on spectral discrimination. Lastly, how much is that? Okay. Neither is easy. And the next, I'm going to show why. So first step, is there something that is a spatial anomaly? That really depends on the contrast between your object and the background, right? So if we have a pixel of a target pixel, and you have a background water, the spatial anomaly is defined by the difference, delta R. And that difference mathematically is proportional to the contrast between these 2 targets, the floating matter and water, and scaled by the subpixel proportion. We call it the He factor. Okay? If he is 0%, then you have no contrast. If he is 100%, the contrast is just the contrast between the floating matter and the water, okay? So how low can we detect? What is the lower detection limit of floating matter? That is related to, first, the contrast, and also related to the sensor's sensitivity. Okay, that's a C noise. And the sensitivity is defined by signal to noise. So to make a long story short, if you have a signal to noise of 200/1, and if you want to use a single band, the lower detection limit is 0.2%. And for Sentinel-2 MSI, the detection limit is 0.8%. So these numbers should be interpreted as, below the subpixel coverage, you have no way to see the anomaly. But above those, you may still have a problem to see the anomaly because you want to use multiple bands, you want to use the index, and that way your noise is higher. But these are the lower detection limit. Now, if we use a single band to achieve the best detection capacity, the first question is, can we detect microplastics? Is there something there? And I think Manuel showed this image already. That's based on thousands, tens of thousands of field surveys. So the highest microplastic density is about 10 million pieces per kilometer square, or 10 particles per meter square. Can we detect this many particles with an optical sensor? Okay. If we assume the average size of microplastic particle of 2.5 millimeter, that's in the middle from 0 to 5, then the subpixel coverage, the He factor, is 0.005%. That is 40 times lower than a detection limit from a 200/1 signal to noise sensor. So that is very difficult unless you really have a huge aggregation of microplastic particles around a front or an AD. And they must sit on the very surface. If they are submerged, we have no way to detect. So that's an extreme difficulty. It's not completely impossible, but very difficult. What about the other floating matters? Well, as long as they are large enough and the sensor has enough signal to noise, you can detect them. For example, these first two images are from the Caribbean Sea, from this publication. And the bottom two images from the Gulf of Mexico. These images show spatial anomaly. At least you know, oh, there's something there. There are some slicks. Okay? The same thing occurs to the Marmara Sea near Turkey. And you see this image of slicks. This is from VIRS. And you also see image slicks of Nova Scotia Shelf of Canada. They have a swirl pattern. You have different image slicks in the Great Salt Lake. If we expand to the entire globe, this is still incomplete, but even though from all these colored boxes and dots, if you zoom in, you can see a lot of image slicks. So these are spatial anomalies. They tell you, oh, there's some form of floating matter on the water surface. And if this is based on OCHI, 300 meter resolution. If you zoom in with a Sentinel-2, with even commercial sensors, you see more, you see better. Okay? So that is quite straightforward if you have the right sensor, if the floating matter is large enough. The next question is, what is that something, if you see something? Okay? That will depend on the spectral shape of that something. And here's the publication to show the spectral shape, okay, of various polymer plastics. What you see is, in general, they have quite a flat spectral shape, okay, regardless of the magnitude. It's quite flat, below 900 nanometer. And there are some features above 900 nanometer, like this one, and 1200 and 1600 nanometer. These are caused by the Kaiser-Harburg absorption. Okay. If you can detect this feature, then you can say for sure, I have some hydrocarbon compounds on the surface. But this would be very, very difficult. Most time we don't have this type of capacity. We have only the visible near infrared band. Okay? And likewise, if we look at this type of material, the spectral shape is quite similar. They are all flat. They do not have narrow band features. Okay? The magnitude changes. And this one, it's a floating, a fishing float. Okay, it's quite the field. Again, you do not have the narrow band feature below 900 nanometer. It's quite flat. And these are not the only materials that are possible on the ocean surface, because we have white caps, we have bubbles. Okay. The white caps may have some features between 500 and 700 if the bubbles are submerged in water. You know, if we have very white surface white caps, they also do not have the spectral narrowband features. They're quite flat. And what else do we have? And recently there's a report of a sea snort in Marmara Sea. If you look at the spectral shape of sea snort, it's right here. It's also spectrally flat. They do not have narrowband features. Okay. So on top of this, we have all kinds of floating vegetation. And Ava, Sargassum, Trichodesmium, and red Nautiluca, green Nautiluca, you name it, and the pumice raft. In other words, there are many kinds of floating matters, including marine litter and floating vegetation and other natural and unnatural matters. But so far, you may see, oh, they are spectrally different, even though there are two large groups. One is this group. They have a lot of spectral features. The other group, sea snort, white caps, float marine litter, they do not have narrowband feature. They're flat, but at least we can separate them, separate these two groups. But sometimes, even though that's difficult, the reason again is because for most satellite sensors, this type of floating materials are very small compared to a pixel size. Most of the pixels have just a few percent or even less than 1% of floating matter in the pixel. So how do we differentiate when they have very low pixel coverage? The trick is to use the difference. So at a low coverage, the contrast between the target pixel and the water pixel, we have seen this in the second slide, is proportional to the full contrast modulated by the He factor. So take this for example. If we do not use a difference, we just look at a target pixel. Okay, the black circle, that's a target pixel, and the nearby water pixel, it's almost the same, except the near infrared for the red edge reflectance. Likewise, for another target, the black circle and the water, okay, they're almost the same. But now if we look at the difference between these two, the difference is green. The difference between these two is brownish. And the spectral shape between these two, the green and the brown, is very different between these two bands, the green band and the orange band. Here is the green ridge. Okay, the 550 has a peak. Over here, the 620 has a peak. So at least you can tell this is some form of a green algae. This is some form of brown algae. And more than that, by looking at the magnitude of this reflectance difference right here, okay, it's 0.002. So that is about 1% of subpixel coverage, because a full coverage would have about 30%. I'm sorry, 0.3, or 0.2 to 0.3 reflectance. And likewise, this is also 1%. So using this technique, we can not only tell the spectral shape difference, but we can also tell the subpixel coverage amount. We can quantify this. Okay? Here is another example to show the previous case. So what are the slicks? If we look at the spectral shape, okay, this is quite flat. There's no narrowband feature. Okay? In contrast, this slick, the 3 points, they all have this pigment feature around 670. We know this is chlorophyll A. Okay? Then based on local knowledge, we know when and where this occurs. This is the likely triple-decimal. And this, we have no idea what that is. Same thing applies to the Great Salt Lake case. Okay? If you look at the difference spectra of 3 points from the slicks, they appear like this. Now we compare with a lab measurements of the what is called brine shrimp eggs. So these are brine shrimp eggs in salt water. Okay? The spectral shapes are almost identical. So this way we can not only classify these slicks as brine shrimp eggs, but we can also quantify density. But when we apply the same technique to a spectral flat spectrum, we have a difficulty. Okay. So these two are the average macro debris and microplastic spectrum. Again, you see there's no spectral feature. And this is a cis-naught. These two are the cis-naught features. They are also flat. Okay. So if we just to see a spectral difference, so is that due to macro debris or due to cis-naught? Or something like this of Nova Scotia. These are the spectral shape. So what exactly is the feature here? We have no idea. We can only speculate. And you may say, oh, this looks like a marine debris. Oh, if there's this much marine debris, you will hear from news report almost every day. But whitecaps can be ruled out because the wind is low and this type of feature lasts for more than a week. But still, we cannot tell what they are. That's the difficulty. So that gives us the biggest challenge. Then you may ask the question, well, you are restricted to below 900 nanometer. What if you use SWIR bands, shortwave infrared bands? And because this has been shown, if you have SWIR band, you can look at those features. That's true. Only when you have many SWIR bands to detect this type of feature here, to tell the depth. If you have just 1 or 2 SWIR bands, those would not help. For example, for the spectral feature of cis-naught, without a SWIR band, you see it's quite flat. If you do have a SWIR band here, what does it tell you? It's low reflectance, that's it. You have no additional information. And this is the MSI spectra for triple decimal. And you see the pigment absorption here. If we include both SWIR bands, here and here, again, other than the low reflectance values, they do not tell you much information. Same thing for the unknown feature here. If we extend to the SWIR bands, they don't tell you much. Okay, that's not against the SWIR band. If you have 3 more SWIR bands around this 2, then you may be able to tell the absorption feature here. Then you can detect, oh, this may be plastics, not something else floating on the surface. So that's the future hope. Then you may argue, what about hyperspectral data? Although we do not have operational hyperspectral sensor, but I know several agencies are planning to launch hyperspectral satellites. Well, they're very useful to differentiate between different floating vegetations because they show spectral wiggling here. If you have more bands, you can certainly tell, oh, they're different. This green is different from the brown, is different from the trickle, is different from red Nautiluca. Okay. But when we apply the same thing to detect marine debris or marine litter, because they are spectrally flat, regardless of how many bands you have. Let's say I add 10 more bands within this. What extra information do you get? Perhaps very little. So it is useful to differentiate different types of vegetation, but less useful for marine leader with hyperspectral for this range. Next is, what if you have a higher resolution? Because you can use a drone, you can use a low altitude flight. I think Shungu showed this. That depends on how close you want to go, or what is your resolution. In this particular example, we detected all those sleek features of Nova Scotia. If we zoom in with the dove, 3-meter resolution, we have this sleek. And further go to 0.5-meter resolution world view, we have the sleek. And the spectral shape is always flat. So even with a 0.5-meter resolution, we can't tell what that is. It's some form of non-vegetation feature. So we can make a speculation, of course. You may say, oh, what if you have this type of resolution? You can see the individual jellyfish on the surface. Well, this would require sub-centimeter resolution, okay, or centimeter resolution. Currently, we don't have. Maybe a drone would have something like this. This is a 2-centimeter resolution. But even though, can anyone tell me if any of these white spots, these are whitecaps, small forms, can any of these white spots be due to marine litter or marine debris or marine plastics? That's just a few centimeters. That's still very difficult unless we have some local knowledge and we have a full spectrum. So with this, I think I can summarize. For our business, size really matters. It's not only critical for the detection limit and for unmixing, but it's also critical for spectral discrimination. Other than the size, most challenging really comes from spectral discrimination because there are many floating matters on the surface, plastics, other non-plastic debris, white foam, vegetation. Especially among non-vegetation floating matters. They are all spectrally similar. This is the real difficulty. But even though, at least we can tell for now, the difference between vegetation and non-vegetation. And the trick is to use spectral difference rather than the pixel spectrum itself. And also use a spectral average to minimize the spectral distortion due to band mismatch. This is particularly important for MSI. If you use a single pixel, you may get all kinds of spectral shapes because some bands have 20 meter, others have 10 meter resolution. They have different portions of the floating meter. Okay? Now, talking about the SOAR bands, hyperspectral or higher resolution, yes, they are useful, but they also have limitations. Depending on how many bands, where the bands are, and what is the resolution. If you can't go into, say, centimeter, you can't tell the morphology, and you still need to differentiate the material based on spectral shape. Okay? All these points are conceptual. I have not even talked about how exactly we implement this concept. I know people have implemented this in one way or the other, but from this, I hope I can show, yes, it's possible to detect a marine leader, but at the same time, we need to be cautious. Detecting something is relatively easy, but discriminating that something is much more difficult. So with this, I hope I showed in very brief message what is possible and what may be difficult. And that's why we have this large team to work on this difficult problem. And I look forward to your questions later.
Excellent. Thank you very much, Chuanmin. It's a very, very nice presentation, very clear messages around. I think there will be some questions, I'm very sure, and it will be very interesting to have some discussion about your approach here.
Sure. Thank you.
Okay, so I think we have just the last but not least speaker today. Else, are you around and ready to share your screen?
Yes, hi, Victor. Can you hear me?
Yes, hello. Okay, well, the floor is yours. Thank you very much for coming in and joining today. I'm looking forward to hear your presentation. Thank you.
Thank you, Victor. Can you see my presentation?
Yes, it's there and perfect. Okay,
great. So I will be talking about optical characterization of marine plastic litter. With optical characterization, I mean that we want to understand the spectral reflectance of plastic litter. And Chuanmin already introduced this in his previous presentation. And I will be showing you some more spectral reflectances of plastic litter. The spectral reflectance is actually determined by absorption and scattering of light by the plastic litter. And for those who are not so familiar with this, I actually compare it also with the human color vision. So our human eye is actually sensitive to the blue, the green, and the red light. So we can say that the plastic is blue, the plastic is gray, orange, and so on. But with a dedicated sensor, such as the one on Sentinel-2, we can look into these colors in much more detail. And we can not only look into the visible, but also in the near infrared and into the short-wave infrared. And this can potentially provide much more information about the plastic litter. So this is not really new. Before we started looking into this from the remote sensing community, there was already quite some information available from optical sorting in the industry. And this is from a publication from 2012 already from Masumi. And at the left, you see the reflectance, the spectral reflectance in the near infrared, the shortwave infrared of different polymer types. And you can see very well the dips. These are the absorption features. And these are very representative for the different polymer types and can actually be used to discriminate between the different polymer types. There has also been research done on, for instance, the influence of a specific label, for instance, on plastic bottles, also influence of the thickness of the plastic and so on. Also in the remote sensing community, we have been analyzing the spectral reflectance of plastic, and we are doing this by these kind of spectrometers, as you see here at the right. It's an ASD spectrometer. You can see also the optical fiber attached to the spectrometer. And these are two examples. At the left, you see from publication from Garaba and Diersen from 2018, where they measured dry virgin pellets. At the right-hand side, you see a recent experiment that we've been doing together with Giulia Leoni from VLIS, and where she was measuring dry karat samples. You see them in the picture here. And if you look at the spectral reflectances, you can see again the same absorption features in the shortwave infrared as we have seen from the previous publication. Of course, if we go into a real outdoor environment, we don't see these real virgin pellets and plastics as I've shown you earlier. This is what we observe in reality. At the left, you see it's a picture taken in Vietnam. It is in a dead mangrove forest, and you can see that the plastic is really trapped into the mangrove forest. So the plastics are really weathered in reality. They have also accumulations of microorganisms, biofouling on the plastics. They have a different structure. So you have bags which are wrinkled. You have plastic bottles which are crushed and so on. So this has to be taken into account if we look at the spectral reflectances. What we have been doing, we have been gathering real weathered samples, for instance, from the Port of Antwerp. And this is an example where we measured with the ASD the spectral reflectance of these weathered samples. So you can see, for instance, the reflectance of a waste rope. There is an orange tube, but also some foil. And again, what we observe is in the visible, it's mainly reflecting the apparent color of the plastic, whether it's green, orange, or red. In the shortwave infrared, we again see the specific absorption features of the different type of plastics. Only when we have quite thin plastic, like the isolating foil of the transparent foil, the spectrum in the shortwave infrared also gets really flat, and you don't see the absorption features are much well pronounced. Same has been done by Garaba and Diersen, where they collected plastic from beaches along the west coast of the USA. And also there in these real weathered samples, you saw the absorption features quite well in the shortwave infrared. Together with Giulia Leoni and within the PlugSim project, we have been doing tests of artificial weathering on plastics, where Giulia used a sun test weathering chamber, and she simulated 1 year of solar radiation in Central Europe. And the graph that you see here is a reflectance of polyethylene, a virgin sample, the original sample in yellow. And then you see a reflectance of the weathered sample for dry and seawater conditions in green and in blue. And you see in the visible that the reflectance is decreasing a little bit. In the first shortwave infrared regions, you see a small increase, I mean. In the second region is more or less stable. Also, the absorption features are still well preserved, also after the weathering. A similar experiment where we simulated the biofouling. So the plastic, they were placed in an aquarium to allow a biofilm to form on the plastic. You can see the samples here in the aquarium on the right. And you see a biofilm here on the carrot sample in the left. Again, an example for a polyethylene sample here. You see in yellow the original virgin sample, and the other colors show you the reflectance with the biofilm for a pristine surface, for a rough surface, and also for wet and dry conditions. You can see a big difference in the visible. We see an overall decrease in the spectral reflectance. You also see an increase in the green and decrease in the red wavelengths. And in the shortwave infrared, you mainly see an overall decrease, but you see that the shape is pretty well preserved, and we still observe the absorption features. Another example where you see also the effect of the structure of the plastic. This is a rope, a blue rope, first rolled in compact conditions, then unrolled, and then tied very tight along a frame. We can see that where the rope is unrolled, you can see the lowest reflect. So these are the blue reflectance. So you can see that they have a much lower reflectance when they are unrolled, whereas in compact condition, they have a much higher reflectance. Of course, in real marine conditions, the plastics can also be wet. They can also be slightly submerged. There is also, like Chuanmin already announced, that there is also organic matter in the water. There are turbidity plumes, there is foam, sun glint, and whitecaps on the surface. And we should, of course, be able to distinguish the plastics from all those. For this, we've been doing experiments in a water tank where we were able to submerge the plastic in the water, but we were also able to add sediments in the water and keep them in suspension. This is a result for a dry plastic orange placemat, where you see the dry reflectance in blue. You can see the reflectance for the wet sample in gray. And then for the placemat submerged at 2.5 centimeter, 5, 9, 12, and so on. And you can see very well how the reflectance in the shortwave infrared decreases. And when it's submerged about 2.5 centimeters, you almost don't see any reflectance anymore. And this is due to the high pure water absorption in the shortwave infrared. You can see a small increase around 1150, and that's actually due to a local decrease in the pure water absorption coefficient. You can also see that the shape in the near infrared changes also due to the water absorption. Also already touched upon by Chuanmin, of course, we have to be able to differentiate the plastic also from the white caps and the foam on the surface. And this is actually a nice example to show you how similar the reflectance spectra sometimes are. So if you look at the black dotted line, this is a simulated white cap spectrum. And then you have the green line, which is a wet plastic bag. And you can see that the shape is very similar. And the same for the wet orange placemat in light orange. And then a sample from a turbid water plume. And also there you can see how similar the two spectra are and how complex it sometimes is to differentiate between both. I will now show you two use cases where I've been working on. The first one is an artificial accumulation zone that we made in a lake in Belgium. And the question was there whether we can detect and also estimate the volume of the accumulation zone. We used a drone for this use case, and we used a MicaSense red edge camera on the drone, which has 5 spectral bands between the blue and the near infrared. This is the accumulation zone on the land. So it was a combination of weathered plastics coming from the port of Antwerp, also some plastics from the Scheldt River and some plastics coming from Vietnam. So you can see as a combination of different types of plastic, but also some wood and some reed, so some organic matter in between. This is a net that we constructed to also contain the plastics on the water and to make an artificial accumulation zone on the water. At the left here, you see one of the drone images, an RGB image. And you can see at the bottom, at the top left, you can see the accumulation of the plastic. At the right, you see the net, which was at that time still on land. And in the middle, you can see some reflectance panel that you use for calibration. So the first thing that we did is we calibrate and derive the reflectance values from the drone images. So the idea was to really derive quantitative information from the MicaSense camera. And then we applied the random forest classification with only 2 classes, so litter and no litter. And this was based on 20 different indices, widely used indices. At the right-hand side, you can see the result. So the white shows you the identified litter, and the black is the non-litter class. So these are the very first results, but you can see that the algorithm already identifies the litter pretty well. It also identifies the reflectance panels, which were also made of plastic, and the nets. You can see a little bit noise at the top right. So this is still something we have to improve, either by improving the training of the algorithm or in post-processing. A second example is where we want to detect individual pieces of litter. And potentially also in the next phase try to identify the litter. In this case, we used a fixed camera setup from a bridge, and we used 3 different types of cameras. So we have a high resolution RGB camera, this one you see in the middle of the box there. We have also a multispectral camera where it was a combination of 2 MicaSense cameras, where in total we have 10 spectral bands. And we have a very dedicated shortwave infrared camera for plastic detection. They were all mounted to point at the same location, and they were also constructed in a way that they were able to measure the entire day. So it was really an automated setup. Some more information on the shortwave infrared camera. We have been identifying the wavelengths that are useful for plastic identification. And we went to a camera manufacturer in Belgium, CSIC, and they constructed a shortwave infrared multispectral camera. They used an in-gas pixel array where they put some filters on top. And in total, we have 6 wavelengths in the shortwave infrared between 1200 and 1700 nanometer. These are some more pictures from the experiment. We used a boat on the water, and we threw some plastic ourselves into the water, not only plastics, but also some wood and some reed. And what we did is we developed an AI model to detect the plastics. The goal was to detect litter. So it didn't make a distinction up till now, distinction between litter and organic matter. And these are the results of the AI model. The boxes these actually show you how the accuracy of the detections for this particular type of litter. So at the left, you see a 99% accuracy. The yellow object was identified with 100% accuracy, and the right target with 55. But still, this 55, we were pretty happy because you can see that the plastic was slightly submerged. Some other results also for this one, I was happy to see the results. It's a plastic bag, you can see here in the middle, which was also slightly submerged, and the algorithm was able to detect it with 100% accuracy. Some more results. So as a take-home message, I think I've tried to show you that the detection of marine plastic litter is quite complex. So you have different polymers, you have different shapes, but we also have to take into account the weathering, the biofouling, and also the features on the surface, such as glint, white caps, and so on. So that means it's not like a simple transfer of methodologies that have been developed already from industrial sorting. So this means up till now, we have been approaching it very simple and tried to do a general litter of detection of floating material. And I show you that this has a pretty high potential. In the next phase, we want to also discriminate further between organic matter and plastics, which I believe is also possible. But it gets really complex if we also want to discriminate between polymer types. In the end, I think if you have sufficient spatial resolution, I think it's beneficial to combine AI, looking at shape, and also spectral approaches. And I believe that more spectral bands, INDIF-NIR, and also shortwave infrared can help. The end, I think we also have to understand very well the use case and choose the right technology for the use case that we have. I showed you two types where we want to look at an accumulation zone and also want to detect individual litter, and where we have selected a completely different type of setup and also cameras. To end, I would just like to announce that we were also doing a feasibility study for a marine litter satellite mission. And we just started with this feasibility study. We will now be doing a large stakeholder and requirement analysis for the mission. So we are contacting a lot of people to get their requirements now. We've been also defining a first mission concept and doing a small mission conceptual design study. So if people are interested to know more about the mission, you can contact me or also my colleague Stefan Lievens. So I want to thank you, and also want to thank our funding agency, the Blue Cluster in Belgium, the ATTRACT program, and also the European Space Agency. Thank you very much, and I will be happy to take any questions.
Thank you very much, Els. Very nice presentation, all of you. Well, I would like to, first of all, thank all the presenters, and we still have about 12 minutes to address some of the questions. They were slow to come, but I think some of them have appeared. If the speakers wouldn't mind to switch on their cameras for the questions, I'll begin to read some of them as they get them from the Padlet. For the first one I have selected from my left, it's for Chuanmin. Hi, very interesting presentation. And this is a question I also had when I was looking at your presentation. It's a question about deriving the delta R. And the question is, do you need to find a pixel that you know is only water surface and covered by litter to compute this difference between something that it's litter and just pure water? And how, I suppose, how do you find that? Where do you put the limit there?
Great question. Nothing is easy in the practical world. So this is about image processing. Okay, it's one step beyond the concept. So how do you find those pixels? you can use some sort of image segmentation technique to first find those features. There's a special anomaly. You can use any technique to find the feature and remove all those non-wanted features, including clouds, stray light. You need to have a way to remove those pixels. Then the difference is water, right? You have the feature you want, and you remove all those artifacts, and then all other pixels of water. You find the water pixels are closest to your feature, then you do a subtraction. So that's, again, conceptual. How exactly you do that? You need to write some codes or call some existing routines from Python or something.
Okay, so essentially image segmentation to identify
right.
Right. Okay, well, it's otherwise they're all in the papers that you have published. So I think details can be assessed there. Another question for you, and sounds very strange, but it's another one I had also in my mind. If you see it so difficult to detect from remote sensing the plastic, what about other approaches? And this question comes along and says, what about extra pieces of information provided potentially by multi-directional, multi-view, and polarimetric measurements? So this is addressing the, okay, we cannot perhaps exploit the visible as we would like. Is there any way out, or would it be worth looking into that direction even?
Well, both Manuel and Shungu have shown different remote sensing techniques, including polarimetry. Perhaps they have talked about. Well, currently, I don't know. I don't know how useful or not useful this additional multi-angle polarimetry may help to differentiate plastics from non-plastics. I don't have an answer, but what I can say is, all I showed are purely based on spectroscopy, spectral shape, how to differentiate. But in reality, we have way more information than this. We know our working environment, and we know wind, we know temperature, we know river flow, and we can get some information from a fisherman news report. So in other words, we know the oceanography or limnology, and those information will be very helpful on top of this type of spectral analysis to tell what it is. So even if I cannot separate, this is plastic, non-plastic, but there's a news report say, oh, on that particular location or neighborhood, there's a report of a marine litter or something. Well, I can say, oh, what I detected is marine litter and some plastics. But those ancillary information is very useful, similar to that polarimetry and others.
Yeah, it's indeed something that we shouldn't be only stuck for this problem into the remote sensing and try to exploit all the wealth of data that we have. I mean, not only even remote sensing on just one technique of remote sensing. And yeah, so
that's right.
Thank you very much, Chuanmin. I really appreciate it. It would signal the way forward. And we have the session on the Friday afternoon where we can discuss this further, and there may be some ideas into making this part of remote sensing as a decade action integrated with INDOS, which is the Integrated Marine Debris Observing System. So remote sensing is just a part of that jigsaw.
Yes.
So, okay, now I have another one for else in this case. And this one is saying that the spectra with dry and wet versus pristine and biofold seem to indicate that water has much larger impact in the spectra than the biofouling. Is this expected, or we should expect more effect from biofouling than measured in this case? So this is asking whether the water attenuation, I guess, has got a higher impact on the spectra than the biofouling. And I know that there is also Shungu who's waiting for speaking. So if else, now that I have read the question, can you answer this or address it somehow, and then leave Shungu to speak a little bit?
Yes, Victor, I can answer shortly. Yeah, in the experiments that we've been doing, we've seen that the biofouling mainly affects the visible light, whereas the effect of the wetness, if the plastics are wet, that it's mainly influencing in the shortwave infrared, which is logical because the pure water absorption is extremely high in the shortwave infrared. Of course, if you go and submerge deeper, you will be also influencing, of course, the near infrared, the red, and so on. But if it's only wet, it's mainly the effect is mainly in the shortwave infrared, and the biofouling mainly in the visible light.
So one would expect that in the visible, you have greater anomalies than being only flat. Flat is probably, if it is equally reflectance in all, it hasn't got any color on top of it, coloration by, say, biofouling of algae or other.
Yeah. Yeah,
right.
Of course, the experiments that we've been doing, that was actually an experiment done by Julia. She used this carrot sample, which were, of course, white or quite transparent, so they didn't have any color attached to it. So we might also have to repeat or doing similar experiments with colored plastics.
Yeah, it indicates that there is a lot of complexity within that separation. Again, it adds this layer of complexity that Chuanmin was speaking about. I think Shungu wanted to have the word, and then we still have time. We're dosifying those minutes.
Yeah, thank you, Victor. So there was a question that was addressed, directed to Chuanmin, related to polarimetric measurements and multidirectional view. And just to add on to that, this is one of the motivations behind the IOCCG task force is to explore all the different types of technologies. And at the moment, we can say, like research is ongoing. So I would say, if you're patient enough, next year you should have some findings that would answer that very question in terms of polarimetric observations, if they are useful, or like how much information they can add to the range of data sets we are getting from different tools and different technologies. I think some presentations as well tomorrow will also discuss some of the different technologies that are currently being used. I think today we have covered optical observations, and for tomorrow, some of the different technologies will be addressed. And polarimetric, yes, observations like studies are being done in lab measurements, and also trying to understand field observation, like field data sets, like satellite observations that have already been conducted. So I would say, again, watch this space, and yeah, keep checking on IOCCG on our website, on publications or data sets that will be available. We should have some answers related to your question. Thank you.
Thank you, Shungu. And indeed, if you have any suggestions or questions, I'm doing the review at the moment on the IOCCG task force on all these techniques. If you have any suggestions about polarimetry, perhaps please contact us. You know who we are. There is another question, more technical, but I would, if you don't mind, Aquile Chapa, I would refer you to contact directly, just in the interest of time. I would stay here and have a more interesting and in-depth discussion, but I am aware that it's a long day for the people in the continent of Europe. It's still early for Americans. I am aware of time is finished almost. There is only just one comment, which I find critical, and it's more about the programmatic part. And it's a question about why do you think, I didn't want to leave this unanswered. Why do you think there is such resistance for investigators to share their data sets? Is this common in other research areas? Does money, funding play a significant role on this? Well, if you don't mind, I'll answer this partly. I think it is because of the difficulty to obtain this data. At the moment, it's all very manual, and it reminds me of initial data from biology or things where it's really, really hard to get those data. I agree with the question that the data should be easily and openly accessible, and it should be a pillar of any further development. So yes, I totally agree. We should be much more looking for cooperation. And with this, I'd like to finish the session, inviting you. Thank you again all for your presentations, for your presence, attendance, and indeed inviting you to the other 2 sessions in this laboratory or satellite laboratory. And I think it would be very nice if you could contribute to this, to our activity for remote sensing of marine litter to be submitted into the United Nations Decade of Actions. So as part of IMDOS. And with that, thank you very much again. Thank you to the organizers and the Air Center. And thank you for the United Nations organization for setting up this event. Have a very good evening and goodbye to all of you.